the flask I've got here and given the size of the gumdrops. Okay, so two critical variables for, actually there are three critical variables for this experiment, or this estimation problem. Critical variable number one is the size of the vessel. What's the size of the vessel?
500 milliliters.
It's 500 milliliters, right? And if you've been through chemistry and you know your chemistry, that means that the volume that I have in the container is 500 milliliters. So several of you took the approach of calculating the volume of a gumdrop, dividing that volume of the gumdrop by 500 milliliters divided by the volume of the gumdrop to come up with the estimation. Pretty good way to do it. And for certain objects, that would be the ideal way to do it. If I were doing cinnamon red hots, those little teeny tiny cinnamon red hots, that would probably get me really, really close, okay? Get me really, really close, because I don't have a problem with what we call stacking, or your volume or packing density. So we do have a packing density problem inside our container. So that's one thing. You have to account for space. So let's talk about the volume. The next variable that I got to worry about is the volume of the gumdrop. These are pretty standard gumdrops. I took a graduated cylinder, actually measured the volume of about 3 or 4 gumdrops, and came out with an average of 2.5 milliliters. You could do it if you thought about the size of your thumb there. So it's a case of that's 2, and some of you could have eyeballed it from a sugar cube. It's about, a standard gumdrop's about the size of 2 sugar cubes. Okay, so a sugar cube's about 1 cubic centimeter, so that could give you a way to do it. So if you were off on your volume of your gumdrop, that probably distorted your answer. Okay, and that probably distorted your answer. So that's one of the things that was a variable. There were a couple of you that accounted for volume, or the airspace, or the space between them. So that's good. The question is just how much to account for. Just how much to account for. So I could classify them in groups. There's a group of you that did between 50 and about 65. Okay, that's a group of you got between 50 and 65. There was a group of you in the 83 to 86 range. That was a pretty good group of you got in that range. Not a bad spot. Then there's the group of you that had 300 or more, or 150 or more. I'll classify it as 150 or more. So that was a group of you. I had 4 of you that I would say were very, very close. The numbers were 96, 97, and 106, and then I think I had a 110 or 111. The 96 one was an interesting approach. The 96 one said at the top of at the top here, you had about 4 visible gumdrops. Used that same top from a packing standpoint and did a packing at the bottom, and looked at the packing at the bottom, and then approximated 7 layers. When they did that, they got 96. The other one was looking at doing more of the packing volume and how much could I really tightly pack something, and that one got 97. And then the 106 calculation was about there. Brandon's the one that got 97, and that's actually the closest to the number that's in the flask. It turns out that now, after a week and after having jostled it around, I probably could have fit a couple more in there. But when I packed it, there were exactly 100 gumdrops in the flask. So it was it's actually been really fun to see the approaches. It's been really, really fun to see the approaches and see how folks tackled the problem. So that's been kind of the approach. And the strategies were, and a lot of you took valid strategies. I mean, I could told you where your errors could possibly be. One is in the packing, how tightly packed could they get. One is in your estimation of the actual volume of the gumdrop. The real fun part, of course, is that I gave you the volume of the Erlenmeyer flask because it's a 500 milliliter flask, and you have to remember that a 500 milliliter flask is a volume. So that was just kind of one of those little kind of But it got you all thinking, and I really appreciate that. Got you everybody thinking. So we're going to do another one, except it's not an estimation problem. This is the one-dimensional motion problem that I talked about. So let's talk about what I'm after so that you guys can actually see it. I have posted it to Blackboard. So this is in week 2, and I will give you an example of what I'm after. So it is a one-dimensional motion problem. So if you go to YouTube and you look up one-dimensional motion problems, what you're going to see is problems. That's not what I'm after. I want you to find a video of something that's in one-dimensional motion. Now, I'm going to use this one as an example. Oops, that's the result. I'm going to show you this one I've actually videotaped and done. I'm going to turn that. I'm going to do that. That way we don't blast everybody out. Okay, so I'm going to see if I can enlarge this. Go to big screen. Okay, so what I've done in my office, everybody know those little pop toys that has a little spring and a suction cup, and you put the little suction cup on, and eventually the spring will overcome the suction and it will cause something to pop? That's exactly what this video is, okay? And basically, if I do this, let's see if I can go back. Escape. Oh, over here. Basically what I've done is yeah.
We are not picking that up on the big screen here.
Let me see this. If it's
now we are.
Okay. This button on this controller is a little different. All right. So basically what I've got is that popper. Hang on. I'm gonna step through it here. Oh, come on. I want to start all the way back. Okay, so basically I have a smiley popper. It's a little ball with a smiley face. It starts right here. It's sitting on this device, and I actually have a meter stick. So you can do this 2 ways. It's up to you how you want to do it. You can actually stage what you have in one-dimensional motion, or you can go and find a video, a piece of video from something that has one-dimensional motion. And what one-dimensional motion is you're traveling in one direction. Even though this one's going to have an arc to it, we can do that ball toss. If I'm really good about doing a ball toss, I can toss the ball, it stays in one direction, and then it falls back down. That's what I'm intending with this smiley, is to do it in one dimension. It pops straight up and pops back down. Not perfect, but it approximates it. So we're gonna do that. So when it moves, it bounces essentially straight up and it comes back straight down. Next week, we're going to actually do 2 dimensions where we're going to account for the fact that it moved in the X direction. This one is intended to move strictly in the Y direction and to come back down strictly in the X direction. But I want you to find or stage. You can do your own video, all right? Could be somebody riding a skateboard. Could be somebody riding a bicycle. Could be somebody on a motorcycle. Could be a horse from the starting gate. Could be the cow out of the chute for calf roping, or the cow out of the chute for bulldogging. I don't care what you do, but I want something in one-dimensional motion. So it's going to go start and go, and it doesn't necessarily have to be at 0 when it starts. You could be looking at a car passing another car, all right? That's up to you, but I want something in one-dimensional motion. So now I'm going to show you what I'm kind of after. So that's what this, I've got a set of PowerPoints here that I've gone through, and I've used that tracking software. Let me go back here. And I will, under resources, is the free video analysis software that I have identified. There's one, it's called Tracker. It is free, but there are multiple out there. Depending on what kind of software you have on your computer, you may have video tracking software of your own. There are a variety of them that are out there. The software that we use in the physics lab here has video analysis software in it as well. You can use the Vernier system. So there's lots of places you can get it, but I wanted to make sure you had at least this one. And this is the one that I used for that smiley software. Or you can just do some estimations. That's up to you, because the way I'm going to grade this is I'm going to grade it 10 points. It's a 50-point problem. I'm going to grade it 10 points for getting the video that's one-dimensional motion. 20 points for the equation of motion that you get for that particular object that's in motion, and then 20 points for justifying your equation of motion. Okay? So, my smiley one, we did the video tracking, used the tracking software, and I got some data. So here's my data. Even though it says X, that's not really X. X happens to be Y in this case, but that's my incremental heights. I've got my time in seconds, so here's my time in seconds. There's my incremental heights, and then I've calculated the velocities for those heights, and I've plotted a position versus time graph. So this is in the Y direction, a position versus time graph for that Y direction. So that's one thing, and then there's my equation of motion. That's my position versus time graph for my equation of motion when I used Excel to give me the equation that best fits that data. So I used Excel to give me that best fit data. So that's the equation of motion that I'm looking for. So we're actually going to do it from a practical standpoint. Then if I go from my slideshow here, so from current slide, so there it is. And then I've written it out off to the side, and we'll talk about how to read the various variables over the course of this week so that you can have that for what you're after. So what I'm looking for is a video and the equation of motion that for whatever object you've decided to stage, film, or you've pulled out of something on the internet. If you pull it out of something on the internet, a YouTube video, a piece of film clip, in a movie, an NBC Sports item, the running back on the football field, whatever, if you've pulled it off of the internet, make sure you reference where you got it from. Okay? Make sure you reference where you got it from, and that will be, because if you just give me a video, if you gave me a video of the running back from the Minnesota Vikings who ran a certain distance, or the guy who ran, or the Oklahoma State player who got the ball and dunked it at the end of that Oklahoma State OU game, I want to know that reference spot. Okay?
So you mean one dimension, does it have to be in a straight line the whole entire time?
Well, or it's something that you can at least approximate it as. Like the ball toss, if you're doing a filming of a ball toss, there is not, to be perfect in one dimension is very difficult.
What about like put one in a machine that shoots it?
Well, if it goes out of a machine, it has to be horizontal. I don't want projectile motion.
Yeah.
Okay? I typically, even though the ball toss looks like projectile motion, we can still approximate it as one dimension because we intend for it to go straight up and straight back down.
Okay.
We'll do 2 dimensions next week. We're going to do this exact same thing for something in 2 dimensions in projectile motion next week. So if you're thinking about it and you're actually filming, you're going, okay, I'm thinking about it and I'm out there and it's a gorgeous day because I know next week may or may not be gorgeous at certain times. I may want to do my projectile motion video, at the same time. Projectile motion is going to be a ball toss in the sense that I'm shooting a basket into the basketball. I'm shooting an arrow towards a target. I'm throwing a ball over a fence. I'm doing a pass over I'm going to have change in motion in both the Y direction and in the X direction. This week, I'm just really focused on just change in motion in one direction. Okay? Everybody kind of understand what we're after?
Yeah.
You guys over in Enid okay with this? Okay. And remember, you guys in Enid are over here on Wednesday. And I forget what the lab is this Wednesday. I'll figure it out. So, motion in one direction. And then you can see that I've got it in terms of velocity versus time as well. And then I also have, just so that, because this question had been asked before, and because sometimes what we have done is disconnected the math from what's going on in reality, how might I ask a question using this data? And so here's some questions that you might see using that kind of data. So that's what we're after in terms of it. And all of those examples, just so everybody's straight, under resources is the video analysis software that I used. Under course material and assignments, under week 2 is the actual assignment. And there's the smiley example. One's a PowerPoint and one is the actual video that I had. Okay? All right. So making it kind of practical. So let's go ahead and start talking about one-dimensional motion. You guys have already kind of done some pre-work about one-dimensional motion, and we'll kind of talk through one-dimensional motion. Now, in physics, I'm going to do this. Let's change it back here. Okay. It looks good. So, when we start talking about in physics, we always tend to start here. We are going to talk about equations of motion, and we're not talking about how this motion occurs. Okay? We start here because these are pretty easy way to get a grasp. We can explain a lot of things that are happening without necessarily having to talk about what's behind it causing that motion to occur. Now, we do know that if I have my pin and I hold my pin up here at the top and I let go, what's going to happen? It's going to fall. We're going to play the gravity game. We're not, at this point in there, we will talk about acceleration, and that acceleration is due to gravity, but we're not necessarily talking about the force or what's causing that acceleration. We are also talking about motion with a constant acceleration. We are not talking about now. When I'm in a car and I put my foot down on the accelerator, right? We call it an accelerator for a reason because I'm actually going to get the engine to get going, to move it and move the car. We're actually going to get that accelerator to get us there. But usually what happens is when we put our foot down on the accelerator, we're very steady acceleration. We don't go, you know, that's not something we do unless our car is doing weird things, right? We do have a chance when that car does weird things. So what we're going to do is we're going to talk about constant acceleration. We are not going to deal with right now if I have something that's going to have a changing acceleration. We're just going to use constant acceleration. And a lot of times that constant acceleration, particularly when I'm in what we usually refer to as the y direction, I'm talking about gravity being the acceleration that I experience. I'm also not necessarily talking about pushing it down with my arm and having that acceleration. Now, I can throw the ball down, but once it leaves my hand, the only acceleration that it has is the acceleration due to gravity because it's left my hand. So there's a lot of times what we're going to do is we're going to break up our problems into various parts. We're going to talk about the motion as I throw it down, or we'll talk about the motion from once it leaves my hand going down. We're going to actually break it out into parts because we have to. The way physicists look at the world is we try to break it into simple ways to look at the motion. We try to bring it into simple models. The old joke is, how does a physicist describe a cow? It's a sphere with the milk evenly distributed throughout. It's not really what a cow is, but we're going to use that from that perspective. We'll actually talk about things that are very massive and very large as point sources. You know, that they're actually down to a point and how that motion is from a point. We'll actually look at that from that perspective because it's a way for us to interpret things. So when we're talking about one-dimensional motion and two-dimensional motion, before we get into what causes motion, we call that kinematics. Kine meaning motion. Okay, so we're going to do kinematics, and that's where we're going to start. So because it's an easy way to do it, we start with one dimension, we go to two, and things go pretty well. So we're going to do one dimension. So in physics, we're talking about matter, stuff, right? We talked last week that kilograms are our units of matter, our stuff. We will get into energy and talking about energy. And I've got a really cool problem for you guys to work on in energy. We got lots of those. We're going to talk about motion, and that's where we're starting, and then we're going to talk about forces. So, chapter 1, we just kind of got our units straight. We kind of got our general frameworks out there. And now we're going to start talking about one-dimensional motion. One thing about our general frameworks, and I'm going to go to the document camera just so that you have an idea. And hopefully all you see is a lovely, pretty piece of paper. We will use two types of coordinate systems. One is our basic good old orthogonal coordinate system, where this is X and this is Y. If I do 3 dimensions, I'm going to do this as Z, X, and Y. So this is Y, this is X, and this is Z. That's our good old orthogonal coordinate systems. And if I put a point out there in that lovely orthogonal system, or a point out here, I can describe this point as X and Y, or I can describe this point as X, Y, and Z. I'm going to zoom out so we can see it all together. My good old orthogonal coordinate system. Now, just because I drew it on the paper in the traditional format doesn't mean I can't move it around. So for example, we like to do this. Physicists love to play with something called the inclined plane. And you will see lots of problems on the inclined plane. So there's my inclined plane. There'll be some angle here on my inclined plane. And we'll look at motion on my inclined plane. And I can do one-dimensional motion on this inclined plane. Because I don't have to be in this traditional X, Y format. I can do my X, Y like this. This is my X and this is my Y. I can rotate my orthogonal coordinate system to allow me to work with the motion either along the plane or perpendicular to the plane. So now I can do one-dimensional motion down the plane. I can do it straight down the plane because I just rotated my coordinate system. So we can rotate the coordinate system. The other coordinate system that we'll play with, I'm still going to use my orthogonal coordinate system to give myself a frame of reference. And if I have a point up here, I can do this in terms of R. That's the distance to my point. And theta, the rotation of that R away from a reference point. So I can write this in terms of R and theta, and these are called polar coordinates. Okay, I can do polar coordinates, and if I want to do it in 3 dimensions, I can have this polar coordinate. I still have an R, I still have a theta, and then I have a phi. So I can do this in terms of R, theta, and phi. Still polar coordinates, but it's another way to look at where and position something. Okay, another way to position something. So we will look at different coordinate systems. And you can translate back and forth between, I'm going to zoom back out. You can translate back and forth between this coordinate system and this coordinate system fairly easily. So if I do that, so let's do my lovely little coordinate system. So here's my point that I'm looking at. And I can have this point in X, Y, or I can have this point in R, theta. R would be the distance between my origin to the point. This is my angle, theta. And now, if I do this, this is where your trigonometry comes in. This is my X, and X, of course, is just going to be R cosine of theta. This is my Y, and Y is R sine of theta. So for those of you who go into the back of the textbook and look at things, right? Go in the back of the textbook and look at things. You look at the fact that sine of theta is y over r. And you look at cosine of theta is x over r. And tangent of theta is equal to y over x. Well, that's all well and good if you're in that lovely, nice, orthogonal coordinate system. So what I do, because I'm going to rotate that orthogonal coordinate system all over the place, is I draw my triangle. So there's my triangle, just like what I had in my coordinate system. Here's my angle, just like what I had in my coordinate system. This is the hypotenuse of my triangle. This is the opposite side from the angle, and this is the adjacent side from the angle. So now my sine of my angle is going to be the opposite over the hypotenuse. The cosine of the angle is going to be the adjacent over the hypotenuse. And if I live with the world like that, it doesn't matter if I turn my triangle like that. I turn my triangle like that. I turn my triangle like that. I don't have to remember which is x and which is y, and I don't have to worry about it. Because I'm going to look at it in terms of opposite and adjacent, and I can keep myself straight. That's how I approach to do it. Each one of you may have a different approach. That's my approach. Because I like to move my triangles around and it helps me go back and forth. But it also helps me deal with the fact that I can actually convert between these two coordinate systems just by looking at my trigonometry. So I can look at that quick trigonometry coordinate system. Okay? So that's one of the things that we are going to deal with. So now let's go back to the computer. So, give it a second. It's thinking about it. There we go. So the first thing that we have to talk about in terms of motion is displacement. Okay? When I'm dealing with displacement, I'm only worried about two things. Where I started and where I finished. Okay? I'm only worried about where I started and where I finished. I don't care how I got there. I'm only worried about start and finish. So that's when we talk about positive displacement. If I choose my number line, I've started at 5 and I've ended at 15. The displacement is 10. Because I'm ending at 15, I'm starting at 5, I only want to worry about that distance in between those two numbers. So I'm only worried about that. So displacement is different than distance traveled. So when we're dealing with motion, we are looking at displacement, i.e. how far did we travel? Okay. From a physics point of view, I'm going to look at that. I'm going to look at the velocity. How far did we travel? And that means where I stopped and where I started. That's that displacement part in the time that I did it. So velocity is going to be displacement versus time. So I'm going to get that to the velocity places versus time. And then I'm going to look at acceleration. I'm going to look at acceleration, and we're going to be looking at that velocity, displacement, and acceleration. Talked about our frames of reference. We're going to use y as up and down. We're going to use x as backwards and forwards. Horizontal versus vertical. So we're going to use that x and y axis to help us. But right now, we're only going to be traveling along one axis. We're not going to be traveling in two axes. 2 dimensions, when we get to projectile motion, that's what we're going to get. And I've drawn 2 arrows on the board. 2 arrows on the screen. Those arrows can be described as vectors. Okay? Vector is a very important concept. Vectors have direction and magnitude. Okay? Vectors have direction and magnitude. So I have to worry about how big it is and what direction it's in. And our book uses, the next chapter is going to actually be looking at vectors and how to add vectors and things like that, and we'll get there. But we want to start dealing with the fact that vectors have to have two things, direction and magnitude. Now, the fact that we're only moving in one direction right now, it's either positive or negative. We're either going to be in the X or the Y. We aren't really kind of dealing with those vectors, but when we get into 2 dimensions, it's going to be really critical that we know that we've got vectors, that they're in 2 dimensions. So my displacement is defined as that lovely change in X, which is equal to where I stopped and where I started. This is different than the total distance traveled. So if I think of displacement, so we can think of displacement in the sense of, I'm in lovely Tonkawa, Oklahoma. Our counterparts in class are over in Enid, Oklahoma. How many ways are there, if I'm driving, are there to get between here and Enid? I can go out to I-35, go down between I-35 to go take 415, take 415 over to Enid. That's one way. I can go out 60 and then go down 74. I could be really creative and go to Stillwater and go to 415 and go over there. If I wanted to, I could go up to Wichita, go over, come back through Woodward and get to Enid. Each one of those ways that I traveled has a different total distance traveled. Some of them are very long, some of them are as short as you can do by driving. If I really, really, really was good, I could fly a direct line between here and Enid, and that's where my displacement would be, where I'm at the end and where I'm at the beginning. So my displacement worries about start and stop. We can kind of look at displacement as a state function. Everybody remember Hess's law. Doesn't matter where I started, and it just matters where I finished and where I started. Doesn't matter whether I went 5 different ways to get there or if I just went straight there. Hess's law is a state function. So displacement is considered a state function. Now I will tell you during this chapter, we're going to be very, very persnickety about the terms displacement and total distance traveled. But as we get later on in the semester, we're going to kind of lose that. Because we're also going to do the same thing with speed and velocity. Because down the way, we'll talk about speed being the magnitude, but it's not. Speed is something different. Velocity is that change in distance or that change in displacement with respect to time. But we all know that, what's my average speed is that's the total distance traveled divided by the time, not my displacement divided by the time. So we're going to have some different terminology, and we have to kind of keep a handle on that different terminology. So there we are. So we're going to start with our lovely little number line that we've got. This is going to show us motion in kilometers. And we start with a little car. And I'm starting with that little car at 0 because it's convenient, right? It's convenient. And we get it to go at some point down the way. And so now its displacement is 14 kilometers. Because I finished at 14 kilometers, I started at 0, and I want you to notice the subscripts. Because we actually are going to use subscripts a lot to help us keep track of things. We will use subscripts a lot to help us keep track. So the final, we're going to use F. We'll also use I for initial. The other thing that we'll use for initial, and I'm going to go to the document camera so you can make it go, is I will do both this. So we will do X sub I, that can also mean our position initial. Or we can do X sub naught, and that's also initial. Both of those are conventional ways of writing my initial location when I'm writing in terms of symbology. Okay? Both of those are common ways that we can use it. So that's going to give me my starting point. So I want to go there, go back. So we got both of those. There. So that's our spot. And so now if I write it out in an equation, that delta means change, So my change is going to be my final minus my initial. We're at 14 kilometers minus 0 kilometers. We are at 14 kilometers is the displacement. So that part's pretty easy. We've been doing this for a while. I mean, we've played with number lines all our lives. So now we want to look at displacement with respect to time. So at time as t is equal to 0, I'm at 0, or I'm starting at 1 kilometer here. I'm not going to start at my 0 kilometers. I'm going to start at 1 kilometer. Then I'm going to be at 120 seconds, I'm going to be at 60 kilometers. And at 240 seconds, I'm going to be at 11 kilometers. And at 360 seconds, I'm going to be at 16 kilometers. I can plot it. So I can find the total displacement. We end up at 16 kilometers. I started at 1, so my total displacement is 15. And I can plot it. I can actually put it in a graph and have a position versus time graph. So I can do that. That's cool. Now, if it's a straight line, I'm traveling at a constant velocity. So being in a straight line, I'll be traveling at a constant velocity. If it's got a curve to it or a parabola to it, guess what? I'm not traveling at a constant velocity. I actually have an acceleration. And we'll use that, but for right now, we're going to travel at a constant velocity. So there's my vector. It has direction and magnitude. The scalar quantity, so vector has direction and magnitude, and then we deal with scalars. Scalars are only the magnitude. So if I look at a vector, a unit vector in the x direction is I, a unit vector in the y direction is j. So let me go back just so we get it. Did I print Chris document camera? And you guys probably saw this in either algebra or, you know, you may have seen it in trigonometry, you may see it right anywhere. If I'm writing a vector, so if I write a vector x, I'm going to do it this way. I'm going to write a vector v. It has a direction and magnitude, and I'm going to represent vector v with a little arrow on it. And I can write it, if it's only in the x direction, I can write it with a unit vector I, which just has a magnitude of 1 that's in the x direction. So 3i would mean I have 3 of these little unit vectors in the x direction, and 3 is my scalar quantity. This gives me my directional quantity. You'll see it with a hat, or you'll see it with a little arrow over the top. I think our book uses a hat. Uses the little caret. If I want to have it in 2 dimensions, have my vector in 2 dimensions, what I'm going to have is, let's do it as 6, and let's put it with a j. J is a unit vector in the y direction, so that would give me my 6 little unit vectors. 1, 2, 3, 4, 5, 6. 6 unit vectors in the j direction. We add vectors head to tail. And so we'll start seeing that pretty quickly. But if I'm writing a vector, I can use this nomenclature. All right? And that's what we're typically going to use from a mathematical standpoint, is that nomenclature. And the scalar only has magnitude, and a vector has direction and magnitude. So we'll get there. All right, so my vector's there. So if I go back, displacement is a change in position. Displacement's not the same as distance. So here's an example of tossing the ball up, showing that it comes back down. We can represent that as one-dimensional motion. So if we throw it straight up and catch it in the same place that we released it, the displacement is 0. It doesn't matter how far the ball traveled, its displacement is 0. So we do have that part. So when I look at my graph doesn't tell us direction. But I can certainly get magnitude out of that direction, because I've got a position versus time graph, because I can do speed. And this is where we start dealing with speed being the change in distance with respect to time. And in this case, I don't have a direction. I just have magnitude. But it also turns out that my change in distance and my change in time is the slope of that graph. Because if I look back at my number line, I have 16 kilometers minus 1 kilometer, and I did it in 360 seconds. I end up with 0.42 kilometers per second, or I end up with 42 meters per second. But I can do that with the slope of my line. Remember, the slope is rise over run. Rise in this case is my change in position. Run is my change in change in time. So my slope of my curve is going to give me my velocity. So I'm going to get that lovely velocity. So this is an average speed. Okay? This is an average speed because I'm looking at the whole distance traveled and I'm looking at the whole time. Now, if that had a curve to it, my average speed could be a little strange. And I want to look at something called instantaneous. But we're going to kind of look at it in terms of, so average speed is any variation in the object's motion. The path length is that total length. The distance depends only on the endpoints. So this is one way to take a position and calculate the distance. And the path length will take on the actual route taken. So I have to worry about that actual route taken. But what? This presentation is on Blackboard. This presentation is on Blackboard. Now, so if I'm looking at it in terms of the x direction, and I know I'm in the x direction, I can get the average velocity. So speed and average velocity is going to have some kind of thing that's related to it. Now my average speed is a scalar value. It doesn't take into account direction, but velocity does. My velocity can be positive or negative. I could either be traveling in a positive displacement or I could be backing up and traveling in a negative displacement. So my velocity may be positive or negative. Time is always positive. If you end up with negative time, you know you've done something wrong. Because we haven't figured out how to go backwards in time. Time is always positive. But average speed isn't necessarily the same as average velocity, okay? Just remember that because we're dealing with different terminology. We're different terminology. Yeah?
I don't understand it because I was looking at the equations. How is it different than speed?
Okay.
Can you give me an example?
The question is, how is it different? Speed is only the scalar quantity. It's only a magnitude.
Okay.
Doesn't care about direction.
Okay.
Velocity can be positive or negative.
Okay, so there is direction.
There is direction. That's the simplest way to look at it. Now the other thing is when we talk about speed, a lot of times when we talk about speed, we're talking about that total path length. And we actually use that definition for speed a lot. So if it takes me, my route that I take from here to Enid is 60 miles, and it takes me 2 hours, my speed would be 60 miles divided by 2 hours, which would be 30 miles per hour. And we use that term for speed a lot. Even though we define it a lot by just using displacement, we actually use the path length being something a little different. So watch it when you're working on Blackboard. What are they actually trying to get? Okay, what are they actually trying to get? And particularly right now, because they're going to be a little tricky, Blackboard will be not Blackboard, but WebAssign will be just a little tricky. And do they want you to divide the time by the total path that you took, that whole 60 miles, or the displacement as the crow flies? It's what? It's about 37 miles as the crow flies between here and Enid. Whether you're using that straight direction or that total path length around. But velocity, when we're dealing with velocity, we're certainly going to be at whether or not we have positive or negative. Because I'm either traveling in the negative x direction or I'm traveling in the positive x direction. So I definitely have it. So velocity has direction. That's the big difference. Velocity has direction. So there's kind of an idea, it shows you that path length piece that's going back there. And we'll talk about, I should get instantaneous velocity. So velocity can be determined by the graph. The average velocity is the slope, and the object moves with a constant velocity. Velocity is a straight line. So we've got that piece. Slope is the change in the vertical axis divided by the change in the horizontal axis. And we do have units, okay? And velocity is going to be in units of distance per unit of time. So it'll be in meters per second, kilometers per second, kilometers per hour, miles per hour. So we can actually show that our units are going to help us out in terms of velocity. They'll actually show us out. So here's our instantaneous velocity. This is in calculus. You guys have been doing limits, right? Everybody's been dealing with limits right now. You're dealing with limits. When I do an average velocity, I take it over the whole time, but as I start to do limits, I start to bring it down, that incremental time. So my limit is going to be my change in x over my change in time. And ultimately, what you're going to see, and this is one of those things where we differ between algebra-based physics and calculus-based physics, is even though in algebra-based physics and calculus-based physics we're going to write it the same way, I'm looking at that change in x versus my change in time, and that's my velocity, okay? So my velocity, my x is going to be where my direction comes from. My time is always positive. We will ultimately see that that change is actually a differential. So it's going to be the differential with respect to x and with respect to time. So this is where we start to see the change between algebra-based physics and calculus-based physics, is we'll start to write it out this way. Okay? We'll start to write out that might get that differential. My instantaneous velocity is going to be that limit as time approaches 0 of that change in x over that change in time. So if I'm doing it on a graph, and I have this position versus time graph. It's not a constant straight line. We know how we can find that instantaneous velocity by looking at the slope of my curve at any given point. So I can actually go in here and I can look at my instantaneous velocity right through here by doing that limit as I start to get smaller and smaller and smaller. And one of your homework problems that you're going to end up doing in WebAssign, it'll have you carry it out to 4 significant figures so that you can see that as I do a change in time of 10 seconds versus a change in time of 5 seconds, that I actually will get a different instantaneous value for that instantaneous velocity. And they'll give you a series of data points. Or they'll give you an equation and you plug in and you solve it for t is equal to 5 seconds, or solve it for t is equal to 7 seconds. Definitely carry it out to 4 significant figures, because they're wanting to show you that as I move along this curve, my instantaneous velocity is going to change. So you'll want to really look at that particular piece. And I'm going to stop there because I'm about to run out of time.